Hello friends, welcome to Abaqus Acumen for quick and sound learning. In today's session, we are going to learn how to do a aluminium can crush test using a Abaqus Explicit. So right now on my screen what you are seeing is a typical 330 ml aluminium can which is get crashed between the two rigid plate. So in this particular tutorials we'll learn how to do a Abaqus Explicit crash test. Also you'll learn how to use different parameters in the contacts, and then quickly we can run this model. So the steps which we are going to follow for this particular tutorials, we'll go through the problem definition for this can crush test, then we'll import the can crush model. So just to save everybody's time, I just done the meshing of initial model. So we'll import the model, we'll review the model, we just have some minimum properties like thickness and metal property. Then we'll learn how to do a step definition in Abaqus Explicit. We'll do a boundary condition for the rigid plates. We'll also do a friction definition and the contact definition. For this particular video we are going to use a self contact, because there are a lot of the crash of the can is there and different surfaces of the can is going to get in a contact. Then we'll do a data check. So in the data checks we'll submit a run for data check. Then we'll also submit a full run. We'll review the results for the can crush test, and then we'll typical output which people looked out of this crash test is like a force versus displacement plot, mainly getting into a buckling behavior. So what is a typical buckling load for this particular can crash test, that will do, and then we'll finish with the overall summary. This problem what we are defining right now. So right now what you seeing on my screen is a typical 330 ml aluminium soda can, and right now on my screen what you are seeing is a typical aluminium soda can for 330 ml can. So typical dimension what you have, you can see this type of can which having a different diameter at the ends, and then they have some steps, and then in the center you have different diameter. So right now in the center diameter is a 66 millimeter, top and the bottom it is a 54 millimeter. Then we have at the bottom steps like a 7 millimeter, at the top we have a step for 11 millimeter, and the center region is 104 millimeter. The units which you are using a SI units, ton millimeter Newton second. For this particular problem the bottom plate will be a support or the fixed condition, top plate will move down by 1 inch, that is 25.4 millimeter, and then we'll understand how this can is getting crushed, what is the buckling force for this particular can. Typically these particular cans are aluminum can, and right since we are more interested into buckling behavior of this can, so right now we are restricting ourselves with only a linear elastic metal property. But in case we have post yield metal information, it is better to put a post yield metal information in the model. Right now we are going to use a linear elastic metal model, and particularly these cans are of a thickness of 0.004 inch, what is available in current market. So that correspond to 0.0102 millimeter. So now we'll start with the first step. In the first test we'll import the uh, can crush model. So this is a basic mesh file which we'll import. So let's first import the model. So we'll go to the file, we'll go to import, and then we have different option here. We'll go to model. So in the model bottom it is Abaqus CAE database. We'll go to Abaqus INP file, and then I'll just go to a particular location where I put a INP file. So this is my can fine mesh INP file is there. In case you want this model for your tutorial, just send us an email at abacusacumen@gmail.com. Will provide this particular model for you. So right now on my screen what you are seeing is a can, aluminum can, and two rigid flat surfaces. The bottom and the top is a rigid surface. So we'll start doing a setup for the can crush. So we'll just first review it. So You can see the three parts are there: applicator, flat bottom, and then part 1 is nothing but a aluminum can crush. Then we'll just review the aluminum property. So since we are using a SI unit, so we have given a density. Since we are running this in Abaqus Explicit, so density is necessary because the inertia forces is going to calculate in this particular model. So 2.7 e power minus 009, which is a turn per millimeter density of the aluminum, and then we are using elastic modulus like a 69 k MPa and the Poisson's ratio of 0.3. Now we'll also check the section property, which is thickness of the aluminum can, which is a 0.0102, which is nothing but a 0.004 inch. And then this particular example, you can see there is excessive distortion of element, so there are chances that you may see a lot of hourglassing. So we recommended like the thickness integration 0.5. In case you want to minimize the hourglass energy, you can go to 7 or 9. So right now we are restricting ourselves to a 5 integration point. So in instances also you can see 3 instances, 2 flat plates, and the bottom is the center can crush test. Now in instances also you can see 3 instances, 2 flat plates, and 1 is a can. Now let's start with the steps. So first thing we'll do is we'll first define a friction property. So you go to interaction property and then you say create. So we'll give a friction value here. So friction type contact, we'll continue, and then we'll go for a tangential behavior of a contact. We'll give some friction value. The frictional formulation, you have different option in Abaqus like a penalty or Lagrangian multiplier. Right now we are restricting ourselves to a penalty method, and then the friction value we can giving is a 1.0. Now friction value 0 is a frictionless surface, 1 is a sticking surface. So very particular to this problem, we are going to the other extreme where we are assuming that it will be a sticky condition between the plates and the cans and the can self contact. But in case there is no sticky condition, you can use a parameter between 0 and 1. So right now we are going with a 1, which is a sticking condition. Then interaction will create a contact, and then we are saying as a general contact, Abaqus explicit what we are seeing, and the contact what we are seeing right now is all with a self. The reason we are going with this all with a self contact, because during the crush of can test there are a lot of chances that the neighboring element will come in contact, and right now we are not in a stage where we can interpret which surface is going to come in a contact. So it's a better and the safe way is define all with a self contact, so you don't have to worry about the what different surfaces will come in contact. Other property we have to assign is we'll give a friction value here, so we assign a friction value to the model. So we're done with the contact. Now we'll give the first boundary condition, so we'll say create, and then displacement boundary condition will give. So mesh, I'll select this particular reference point for the rigid. So once I given a boundary condition to the reference point, it applied to the all rigid plates. So this bottom rigid plate is made up of R3D4 element. So I'll just pick up that reference point, and then I give all boundary conditions. So I fix the bottom portion, then we'll go and do a step definition. So I created a step, we'll give the name Aluminium Can Crush, and we are going to run with a dynamic explicit. So moreover we are going to run this as a quasi static problem. So we are going with a dynamic explicit. Then in dynamic explicit you have to give what is the end period. Now end period what we are giving is a 0.01 second, which is nothing but 100 millisecond. We are giving a 0.1 second, which is nothing but 100 millisecond run. And some description you can give, can crush test. Now this particular end period is means whatever the vertical plate displacement we are going to apply, so it will start it from 0 time, and 0.1, which is 100 millisecond, the full displacement will be applied. Now since we are modeling this into a quasi-static problem in a dynamic explicit solver, so the time period selection should be based on such that this particular time should not be in a closer to the frequency of the object or the frequency of can. So in that case you may see a resonant condition in can, and that you can see there are a lot of dynamic forces are coming and the kinetic energy of the part is going high. So we already done all this calculation at the background, and then we found that 100 millisecond is a good enough for going for this crash test. So we are giving a 0.1 second. Now we fix the bottom plate. Now we have to apply a displacement on the top plate. So I'm going to give one more BC. I'll go again to the BC panel. I'll say create, and I'll say displacement, and then you see it will be in select in the steps aluminum crash test. So continue, and I'll say mesh, and then I'll select this point, and then I define all zero vertical. I'll say minus 25.4. I need to, because we are running in the Abaqus Explicit, we need to give amplitude. So I'm making a tabular amplitude here. So I'm saying for time 0 amplitude will be 0, and for time end, which is 100 millisecond, it will be 1. So at 0.1 second all 25.4 displacement will get applied. So done. You have to connect the amplitude to your load. I say OK, and so you have applied a load. So I'll just go back to our steps. So we imported the model, we reviewed the model, we've done a step definition, we put a boundary condition, we given a friction value, we have defined a contact definition. Now we'll go and then create a job, some name, and so we'll not submit right now. We'll do a data check. So we'll go to the manager. So in manager you have different option: write input file, data check, and submit. So we'll do first data checks. Once we get a confidence in a data check, we found there is no error, everything, then we go ahead and submit a run. Now we'll do a data check. So I'll just click on a data check. So in data check it will check whether there is any error in terms of preprocessor or something is missing. So I just submitted for data check. The other things I want to just tell to you is mainly important to like outputs. So you can alter the outputs, number of intervals, or you can change whatever outputs required for this. Or in terms of if you require a very refined output in terms of history, that also you can change. You can change the interval to get a more refined output in terms of energy or contact forces or contact details. So right now we submitted for the data check. So tutorial can crush.inp is submitted for data check. So this particular file, so whenever you put for data check, it go to like a working directory or the temp directory. for my particular case I set it to a working directory, but for your case it may be going into temp directory. So it's better to go and have a look in a temp directory on how the model is look like. So we'll just quickly check how the tutorial model looks like. So I just open the model in a text pad. So you can check by star. So stars are command in Abaqus. So you see a part name, then you see a node, then you see a element type. What we are use for rigid string is a R3D3. Then you see the flat bottom, the node definition same is again R3D3. Then we have a can aluminum can, which is having node definition, which is a 4 noded shell element. R stand for reduced integration. Specifically you can see the shell section where we are define a thickness. Again the integration point is very important when you do this type of analysis, mainly from hourglass point of view. In case you see some hourglass or artificial energy getting into your model, we suggest you to go for higher integration point. Then you see assembly, different element set. This is what is amplitude we are defined, how our load is going to get applied. Then there are all these metal properties of aluminum. We have density, elastic modulus. On the surface interaction side, we have defined a friction 1, which is a sticking condition. Again, based on your experience, you can change it from 0 to 1. And then this is a all self contact. So we define a contact, OP is equal to new contact inclusion all exterior. We are also connected the contact property, mainly friction. So this is connected to the contact. Then we are getting into a step definition. We are given a 100 millisecond run. Then is a typical default bulk viscosity. We are giving a displacement of a 25.4, which is nothing but a 1 inch. And then we ask for output. Now let's check where is our data check gone. So friends, now let's check the result of this can crush test. So I just imported the ODP file. So let's simulate it. So what you can see, after some displacement, this can is getting crushed here. So let's check into some other parameter like a displacement. Let's check the displacement. So I'm checking the field output. So let's check what is I just plotted a magnitude. So let's set the legend to 14, and that's so fixed. So you can see right now how this can is getting crushed. So you can see there's somewhere in the middle the buckling start and then whole structure collapse. Now friends, let's quickly plot the force versus displacement diagram. So that way we'll get understanding what particular load level this is structure is got buckled. We can see the buckling start somewhere here where my cursor is there. So let's check what is a buckling force. So for buckling force, what you have to go, you have to go to XY data. So you double click on that, go to ODB field output, continue, and then reaction force, you say magnitude. You can also the magnitude and the vertical RF3, the force will be same because the plate is constrained in all directions, just moving down. So it's okay to select magnitude. Also the plate displacement will check, so it's okay to select magnitude. So all except Z, everything is constant. So we'll say unique node, position is unique node, and go to element and node set. We know the referral point applicator, so I'll say plot. So what you can see right now in plot, like you have red color reaction force which moves up and then it drops down. So the reason for dropping down is structure getting buckled somewhere around a 350 Newton. So let's also plot a cross plot. So to get a cross plot for force versus displacement, go to operation data, continue, and then you select operator combine, you select magnitude and then reaction force at a data expression, and then you just plot the expression. So you can see now there's somewhere around 350 Newton force and somewhere around the 12.5 millimeter displacement structure get buckled, and then this is a post buckling behavior. Now if you run this into Abaqus standard, it's very difficult for implicit solver to get a post buckling behavior. So in explicit you can easily get a post buckling behavior, and then you can see the load is getting dropped as the cone is getting crushed. So friends, just to recap in today's session. So friend, just to get a recap, in today's session we started an aluminum can crush test using Abaqus Explicit. So just to save everybody's time, I have a mesh model. In case you want this mesh model, just email us at the abacusacumen@gmail.com. We can provide this particular model for your practice. So we built a model. We use a linear elastic aluminum property. The bottom plate is fixed, top plate we have pushed it down, and we also define a self contact, so all inclusive, because in this particular problem we don't know which particular surface is going to come in contact. Also there was a lot of self contact between the can. We use a friction value 1, which is a sticking condition. You are free to use whatever the friction value you want based on your experience from 0 to 1. And unit what you use is a SI unit. Then the other thing is we use the can thickness, which is right now available in market at 0.004 inch. Also we plot the force versus displacement diagram. So friends, go ahead, practice on a cache current test using Abaqus Explicit, so you'll get some hands-on on Abaqus Explicit. So this was a building up video on the Abaqus Explicit. We are going to come up with a lot of videos for Abaqus community. So if you want to really get more information on the upcoming videos, please subscribe us at Abaqus Acumen on YouTube. Thanks for watching this video. Thank you. Bye bye.